Time, if you cannot see my screen, please inform me. I will share the screen with you. Yeah. Also, if you have any doubts, you can ask on the chats. I will check after every 10-15 minutes, I guess. So I will respond in that. And if you cannot see my screen, do inform me by unmuting yourself. Okay. So, okay. So my slide should be visible. I'm starting. So, what is our today's agenda? Just a second. I will remove this from the slide. Yes. So, topics to be covered are modular arithmetic, binary exponentiation, matrix exponentiation, and some of their applications. We will be covering. Also, prerequisite is just that you should be having basic idea about how matrices are multiplied and those things. So, I had shared the document, I guess, in the resources, but still I will be discussing in brief what is it. So first we will start with the modular arithmetic. So what does modular exactly means? I hope these two definitions are clear with everyone. Still, I will tell once more. What is the meaning of divisibility? So divisibility, also written as A divided by B, as written in the symbol there on the right hand side. So A divisible by B means that you can write A as B into C. So where C should be an integer. So if A is divisible by B, then you can write it as A equals B into C, right? This is simple definition of divisibility. And what are prime numbers? So prime numbers are those numbers which are divisible by only one and the number itself, right? No other divisible divisor less than P is possible other than one. So when I say A mod n, we are basically referring to the remainder that we will get when A is divided by n. Right? So when I write A mod n equals R, so basically we have a number, we have an integer d where we can write A is equals d into n plus R. This result is very important, right? So like you can write A equals d into n plus R when you have A mod n equals R. Just remember this. So if this is not clear to anyone, because this is very fundamental, you can say right now. I guess this is very trivial. That A is divisible by n, giving a remainder R. Right? Now we will come what is equivalence relation. So equivalence relation is basically you must have studied in class 12th or 11th, I guess. So it must follow three properties, right? Equivalence relation. So I claim that the modular operation is equivalent under this symbol, right? The triple dash symbol. It's a equivalence relation. So basically, it will follow these three properties: reflexivity, that is A is always congruent to A mod n. That is, when you divide A by mod n, you can always get you will get the same remainder as A divided by n. So yeah, okay, let me clear this symbol. I guess I have not described this. Hope you are able to see my notes. I will share the notes. So if you are not able to see the screen, just tell me once. Right? So if I write A, just so A congruent to B mod n, right? So this is basically equals A equals D into n. So let me write D in n1 plus some k, and B is also some D2 n plus k. That is, when you divide A and B both by n, they must be leaving the same remainder k. Then we write that A is congruent modulo under B, congruent modulo to B under n mod n. Right? So this is most important definition. So this symbol is creates a equivalence class. So why this creates an equivalence class? Now I will say. So first property will be the reflexivity. So I say A congruent to A mod n, right? This is pretty obvious because A and A will always be the same remainder. What is symmetric property? So if I say that A is congruent to B mod n, so it will also imply that B is congruent to A mod n. So this is also pretty intuitive because they are leaving the same remainder k as explained here. And the third part will be that A congruent to B mod n and B is congruent to C mod n. Right? If these two conditions are satisfied, then I can say that A congruent to C mod n. Right. This property is known as transitivity. Right. This completes my equivalence relation class. So why is this happening? So like if I write A is n into d1 plus k, B is n into d2 plus k. This is basically coming from the this first relation, right? A congruent to B. And from the second relation, we say that B and C should leave the same remainder. So C is n d3 plus k, right? So now you see these two, they are leaving the same remainder k. So obviously A is congruent to C mod n. Right. So this will be satisfied. So hence we have a equivalence relation. So why is this equivalence relation important? This equivalence relation is important because this will be dividing your entire number system or the space on which you are doing the modulo into n classes, right? So like if you have 1 to 100 and you are taking mod 3, so entire numbers from 1 to 100 will be divided into three classes: 0, 1 and 2. That is those which leave remainder 0 with 3, those which leave remainder 1 with 3, and those which leave remainder 2 with 3, right? So this was the equivalence relation property. And on the right hand side you can see some of the properties that are followed by modular arithmetic. So if you are doing A plus B modulo C, then this is same as A mod C plus B mod C whole taken mod C, right? So why is the outer mod C important? The outer mod C is important because if the both the remainder A mod C and B mod C are adding up to be a number greater than C, which is quite possible. Say A gives a remainder C minus 1 and B gives a remainder C minus 1, then you have the total remainder 2C minus 1, which is greater than equal C, right? So we take a mod C to get the final remainder, right? So similar properties followed by multiplication also. A into B mod C will be A mod C into B mod C, and also with subtraction. So subtraction we will be adding a plus C. This is because suppose A is giving a remainder 0 and B is giving the remainder C minus 1. So we get a negative modulo, but remainder should be positive, right? So we add plus C to get the remainder positive, which is correct because C is always divisible by C. So adding C doesn't make any difference. But this last one is a little different. So A divided by B mod C, it's not A mod C by B mod C, right? So this is A mod C by B mod C will give you a floating point number, but we need an integer. So what we do is we do that we take A mod C, but we multiply by a modular inverse operator of B under modulo C, and then we take a product modulo that is shown in the point number 2, right? So what is inverse modulo? I will be describing it later, but basically you can say that uh, so basically if you have a number A and X is its inverse, then this property will be satisfied, right? This property you should keep in mind. So X will be inverse of A under mod N. So if this property is satisfied, that is A into X congruent to 1 mod N, then we get an inverse modulo. So we can also write is that X is basically congruent to A inverse. So when we multiply by B, then we get Bx is equals congruence to B A inverse. We can multiply the same numbers on both sides when we are doing congruent modulo. So B mod A. So this is basically equivalent to what we are doing as B by A, right? So hence we are taking the inverse and doing a product with it. That we can see, right? So some major theorems in modular arithmetic. I have written quite many theorems, but you don't need to go through all of them for Div 3 level. Chinese remainder theorem especially is used in Div 2, I guess. So I will give this first three properties which are very important. So Fermat's little theorem, it's very simple theorem. It says that if P, yeah, you should make a note whether P is prime or it is written any number. This Fermat's little theorem and Euler's theorem has this distinction. I will be showing that. So Fermat's say that if P is prime, then A power P will be congruent to A mod P. So now A can be any integer, but P needs to be prime. So this is the first theorem that you must remember. It can be easily proven by contradiction. You can find the proof on Wikipedia. I will link the resources. So, but this is you must remember this fact. So A power P is congruent to A mod P, right? And second theorem is N. Euler's theorem. So if A and N are co-prime integers. So what is co-prime integer? Co-prime integer basically means that the GCD of A and N should be 1, right? Basically they don't have any common factor. So like it both doesn't need to be prime. So I will give you an example like say 6 and 35, right? 6 and 35, both are composite numbers, 6 and 35. But you see that GCD of 6 and 35 is 1. So we say that they are coprime numbers. So when we have two coprime numbers, A and N, then we can say that A powered phi of N. Phi of N, what is phi of N? Phi of N is the Euler-Totient function. So Euler-Totient function, how is it defined? Yeah. So Euler's Totient function phi of N is defined as number of numbers less than n which are coprime to n, right? So number of numbers less than n which are coprime to n. So I will give you some examples like phi of 2. Number of numbers less than n which is coprime to n is 1, right? Only 1 is coprime. For phi of 3, 1 and 2 both are coprime to it. So we write phi of 2. Coprime you understand, right? So I'll just give the definition. Coprime means GCD of A comma B equals 1. Then A and B are coprime. So yeah. So what will be phi of 4? Phi of 4 is basically 1 and 3 are coprime to it. Right? So 1 and 3 are coprime to it. So phi of 4 is 2. Right? So how do we find this? So Euler had given the formula. So if you have a number, say a number n, so we can write it as p1 power e1, p2 power e2, p3 power e2, a3, and so on up to pn power an. So let me make it k. Yeah. So p1, p2, p3 are distinct prime numbers, right? These are distinct prime numbers. So what will be phi of n in that case? Phi of n for general number will be n into 1 minus 1 by p1, 1 minus 1 by p2, under dot up to 1 minus 1 by p5. Okay. So this is the general formula. You can prove it, but I would not say that you need the proof at this moment. You just remember the formula. You can reduce many numbers into formulas which convert to phi of n. So this is a very important formula. So does this work at all? So let us see for phi of 2. So I say that 2 has only one prime factor. 2 is basically 2 power 1. So we don't need any other thing. So 2 into 1 minus 1 by 2, right? So equals 2 into half, which is 1. So let us see. Yeah, 2 into half is 1. Right? So similarly, if we see phi of 3 equals 3 into 1 minus 1 by 3 equals 2. Yeah. So this is okay. Yeah. So this formula is correct. Right? I hope everyone has understood. Is there any doubt? Is there any doubt up till this point? Any doubts? No, I guess. Cool. So these are the two major theorems. One more theorem is the Wilson theorem. Not that important, but you can go through it. So basically it says that if n is a prime number, so here we are considering only prime numbers, then this property will always be satisfied that n minus 1 factorial is congruent to minus 1 mod n. Or in other words, we can simplify this to this thing. So, yeah. So Wilson's theorem is basically saying that n minus 1 factorial plus 1 is divisible by n. But is it true? Let us see for say 3, right? 3 minus 1 factorial plus 1. What is this? So 3 minus 1 factorial is 2 plus 1 equals 3, which is divisible by 3. So this theorem is correct, right? So this is one of the good checks for prime numbers, right? So these are the three major theorems. You don't need to give much importance to Lagrange theorem at the moment. Chinese infinity theorem is an important theorem, but you can consider it at a later point. So yeah. So now let us go to modular inverse. So I had given you the definition of modular inverse as a into x congruent to 1 mod m. If this condition is satisfied, then we say that x is the modular inverse of e. So there is a theorem, there is a method for finding GCD given by Euler. It's known as the extended GCD theorem. I hope everyone knows about it, but if they don't know, I will explain it once again. Actually, it's very simple. So if it is said that if the GCD of, so this is extended GCD. So if GCD of E comma B equals G, right? So it said that you can write G as Ax plus By, right? You can write this. But how can you derive this exactly? So the process is that, so I will give you an example to demonstrate the process. It's not that intuitive. So like if I am finding the GCD of 6 comma 4, okay. So how will you find the GCD of 6 comma 4? GCD of 6 comma 4 is basically GCD of 6 minus 4 comma 4, that is 2 comma 4, or this is also GCD of 2 comma 0. So why we did this? This is because GCD of 2 comma 4 minus 2 into 2. I hope this is very clear. This process, I guess this was taught in the school. So hence, since one of the term is 0, I can claim that my GCD is 2. This was the Euler's method of finding GCD, right? So what we do is that we just reverse calculate. So we say that um, from the bottom we have 2 into 1 plus 0 into which is 0 equals we have 2, right? So what? How did 0 come? 0 come as 2 into 1 plus 4 into 4 minus 2 into 2, right? From the previous step, I'm seeing how did 0 come here. So I just revert this. Now what I will do is that I will be combining this 2 and this 2, right? So I will get 2 into minus 1 plus 4 into 1 equals 2, right? So now my question is, how did this 2 come? I know about the 4 because I had in the starting. So, but how did this 2 come? So this 2 come because of this term 6 minus 4. So I will be replacing this with 6 minus 4. So it will become this. Now again, I will combine this term and this term. So I have 6 into minus 1 plus 4 into minus 1 into minus 1 will become 2. So 4 into 2 equals 2, right? So now see that I had my terms as GCD of 6 comma 4 as 2, right? And I am representing this by the same terms 6 and 4, right? 6 into minus 1 plus 4 into 2 equals 2, which is the GCD. So this is basically the Euler's extended theorem that for any number if GCD of E comma B is equals G is basically GCD of A comma B, then you can write A into X plus B into Y equals G, where X and Y are some integers, right? Some integers, they're element of integers. So this has formal proof, but I will not go through the proof at the moment. You can again look it up on the internet. So I'm now taking that as my pre notion that we have. So I'm saying that if GCD of A and M is 1, right? So that is Ax plus My equals 1. It can be written because I see that GCD of A and M is 1. Then if I take modular M on both the sides, what will I get? On the right hand side, 1 mod M will always be 1, except when M is 1. So when M is 1, you cannot even find the inverse. So I'm assuming M is not equal to 1. So I'm taking mod M on both the sides. What will happen that the M part will disappear because it's obviously divisible by M. Hence, and what we will be remaining with A dot X, A into X. So into X is 1. So we get the modulo of M. So what we will be doing is that we will be finding the GCD of A and M and obtaining the values of X and Y. Right. Once we get the value of X and Y, the X will be our answer to the a modular inverse of A. So as you can see on my right hand side, extended Euclidean is the function that will return my X and Y by taking the input parameters A and M. So X and Y will be passed as reference. For the code, you can refer to. Okay, I will be uploading the resources of extended Euclidean, but I guess you should have come up at some time before also. It's okay. So let's see. Yeah. So once you get back X and Y, you see the GCD. Obviously, if GCD is not 1, basically M and A had some common divisor, then obviously there is no solution because you can I had already shown that when A and M are co-prime integers, then only you can okay, this can be proven that when A and M are only co-prime integers, then only you can find the modular inverse. Otherwise, there is no point in finding the modular inverse. So GCD that will be returned will always have to be 1. This was our starting assumption also. Otherwise, you can find. And once you get back the X, you just need to ensure that X is under modulo M. Because as I showed here, you see that here we had got -1. So if X is -1, then we will not get basically the modular inverse. So modular inverse always needs to be positive integer. Hence, we do that plus m to bring it into the positive domain, and then again take modular m so that if it was greater than m, we bring it down to 0 to m minus 1. So this is one way of finding modular inverse, and most widely used method of modular inverse, because most of the time you will be finding modular inverse is when m is prime. So once m is prime, we can make use of the Fermat's little theorem, right? What did Fermat's little theorem state? That a power p is congruent to a mod p, right? If p is prime. So what we will do that we will multiply both sides by a power -2, right? So what will happen? Once you multiply by the same number, you can add the powers as usual you do. So a power p -2 is congruent to a power -1 mod p. Right. So you see here, we got the inverse that we were finding. E power -1 is basically our inverse. So we say that e power -1 is congruent to e power p minus 2. So basically, we will be using this here. You can see on the second statement, e power m minus 2 is congruent to a mod m. So if we just calculate e power m minus 2, we can get the answer. So how will be calculating a power m minus 2? Usually m is very large, of the order of 10 power 9 plus 7. So obviously we cannot multiply one a into a into a. We'll be using binary exponentiation, which will come later in the session. So I will not explain how we will do that. But just remember that e power minus 2 m minus 2 will return you the modular inverse. This is most widely used method. Also, for if there is any arbitrary modulus, instead of using the GCD part that we did now, we can use the Euler's function. So Euler's function was defined when a and m were co-prime numbers, right? So it doesn't depend whether m is prime or not prime. Just we need that a and m are co-prime, which was also the same. Sorry, just a second. Which was also the precondition for modular inverse using extended GCD, right? So instead of using that, we can use the Euler's function that a power phi of m minus 1 is congruent to a power minus 1. How did this come? This is also very simple. So Euler's function stated that e power phi of m was congruent to e power phi of m was congruent to 1 mod m. So again multiply by a inverse on both the sides. Yeah. So in this part you get A inverse, and in this part you will get a power phi of m minus 1. Hence, the a power phi of m minus 1 will return you the modular inverse. Also, there is a trick that if you are finding, like you are computing NCR and NPR, most of the time you will be seeing that you are multiplying by all the numbers from 1 to m. Inverse of all the numbers from 1 to m. So what we can do that instead of doing this every time. So binary exponentiation complexity will be log of log of m. No, the power, log of power. So instead of doing it in m log m, because you for the m numbers it will take log m each time. So instead of doing that m into log m times, we can finish it within O of m times. So this is, you can just memorize this function. This is a formal proof which you can see on CP algorithms website, but you don't need to care about the proof. Basically, you can do this in O of m time, linear time. Right? So this is all, I guess, for the arithmetic modulo. Yeah, this is all. We will be doing some questions at the end. So if you have any doubt, you can just clear it now. If no- Any doubts? Anyone? I guess. Okay. Cool. So we will be moving on to binary exponentiation. Just a second. My screen is visible, right? Yeah. So let's start with binary exponentiation. So what is binary exponentiation? Now let's see. Just change my screen. So like if you are finding a power b, what is the most common approach for us? A into A into A into A, do this for B times, right? So we will multiply this for B times and take the. But is this feasible? This is not at all feasible. Like if B is of the order of 10 power 9 plus 7, you can only do 10 power 8 computation at max 10 power 8 computations in 1 second, and you need to do lot many other processes also with this number. So this doing 10 power 9 plus 7 only products is not feasible for us. So what can we do instead? We can do instead that, say we need to find a power 4. So what can we do with a power 4? So a power 4 is basically a power 2 times 2, or we can also write it that this is e power square whole square. So if I had known the value of a square previously, so I could have reduced to a power 4 in just one step, right? So if I pre-compute a square's value, I can find e power 4 in just one step. Similarly, if I know the value of a, I can compute the value of e power 2 in one step, which is also trivial. So instead of doing this product 4 times, I have reduced it into 2 times, Right. In just 2 steps, I can find the e power 4. So I reduced it log 2 of 4. Right. 2 steps. Again, but what would have been if the power was odd? So if the power was odd, I can just take one number a out and again write it as e power 4 and follow the similar process. So this was basically computed in the same step. So we were doing like a plus, a into a square into a square. Right. So this is one step. So the number of steps didn't increase, only just a product part increase. Number of steps remains the same, just a product calculation increased in this thing. So what are we actually doing here? We are doing here that if we have a number p, so p can be represented as in the binary number as b0, b1, b2, dot 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 up to bk. So where B is the Bi is the most significant. B0 is the most significant bit. Uh, B0 is the most significant bit. So this is the binary representation of P. So binary representation. Hope you know what it means. So like I will show you for 5. So it was the binary representation of 101. Right, base 2. So we are doing that. We are computing for every power of 2 what was the value of AI and taking the product of only those powers. So like a power 4, I know it is required since its bit is 1. Similarly, a power 1 is required since its bit is 1. So this is actually what we were doing here. Right. So for any number, like for if I take 11, so 11 will be written as a power 1 0 1 1, right? So 1011. So base 2. So what is this basically? So we need e power 8. This is in 8th place into we don't need e power 4. We need e power 2, we need a power 2, and we need a power 1. So you see that there are only log to the base 2 bits, hence we need log to the base 2 product terms. And if we pre-calculate these terms, then you can do this in one step. So at max, your recursion tree will go down to log of base 2 to the power of to the power bits. So see that there is a significant reduction. Earlier we were taking O of p time to calculate the power when we were doing product a p times, but now we are just taking e to the log to the base 2 to the log p to the base 2 steps O of. So hope you are clear with this thing, why it is log to the base 2. Any doubt here? This is basically because we will be breaking down the power into its binary and taking those terms which are set to the bit 1 and just taking their products. So hence we will take log 2 steps. Also, how can, like if you start computing, like first we will compute e power 8, then we will compute e power 2, and then we will compute e power 1, it will then again reduce down to O of p. Instead what we will do, that we have computed e power 2 from e power 1 by doing a into a. Similarly, we will compute e power 4 from e power 2 by doing e power 2 into e power 2, since e power 2 was currently computed. Similarly, we will do e power 8 as e power 4 into e power 4, since it was recently computed. So you see that they will be at max log to the base 2 steps. Right, log to the base 2 steps, and in each step you will be taking the product terms. So this product a into a will take O of 1 time. So we don't need to consider it. So hence we will take log to the base 2. Means there is no extra overhead of again finding e power 8, e power 4. So I have demonstrated this with an example. So like I am trying to find, yeah, so let us see what we have written. Yeah, so like as I had said, if we are finding e power n and we are doing product e in times, it is not feasible since it, for large n it will take a lot of time. So we are reducing n in its binary. We are splitting the power in its binary form. So like if we are finding 3 power 13, so 13 is written as 1101. So we are taking 3 power 8, 3 power 4, and 3 power 1, since these bits are set in the binary form of the power. So how we are computing this powers? So first we have 3 power 1 is 3. Then we are just doing 3 power 1 into 3 power 1 to get 9. Once we get 9, we compute 3 power 4 is 9 into 9, 81. And finally 3 power 8 is found as 81 square, since 81 was recently computed. So only we need log to the base 2, sorry, log to the base 2 and steps. So what will be our final answer of 3 power 13? We will be just taking those terms which had bits at 1 and just take the product of them. So this is done in O of 1. O of 1 into O of log 2 to the base n. So log n to the base 2. I hope you get the idea of what we are doing in binary exponential. So most of the time you will be not being writing the code from the scratch. I will show you a snippet of it. You can save the snippet because this snippet will be used most of the time. So just don't try to memorize it. So this is the formal definition of the binary exponentiation, what we were doing. So if n is 0, we will return 1. If n is even, we will pre-compute a power n by 2 and a power n by 2 and then just square the results. And if n is odd, we will multiply a once and then once we take out 1 power of n minus 1 will be even. So we will compute n minus 1 by 2 and n minus 1 by 2. So in each step, we are reducing the power by 2. Hence, we have log n to the base 2 steps. Yeah. So implementing this binary power has two approaches, the recursive approach and the iterative approach. You don't need to see the iterative approach now. The iterative approach is a bit faster, but I will explain the recursive approach since it is very intuitive, from the definition. So let us see, compare it with the previous definition. So what was our base case? Base case was n equals 0, then we have 1. So we see that if b equals 0, b is the power, we are finding a power b. So b is equal to 0, we are returning 1. Now next case, if n is even, then we compute e power n by 2 and just square the result. So what we are doing then, so we see that if in both the cases we need to find n by 2 floor values, right? So when we are doing integer division of b by 2, we get the floor value. So instead of computing that separately for two parts of the odd part and the even part, I'm getting the binary power of a power b by 2 directly, right? So we are getting the power of e power b by 2 directly from result. So once it is pre-computed, we don't compute it again in the future. Instead, what we will do, that result into result, if the number was even, and result into a, this this part into a comes from the last factor if it was odd. So I guess the function is pretty easy to implement, and it comes from the definition. Just remember the definition, you can implement the function very easily. Iterative version is the same thing implementing, just using bit shift operators. So it is a bit faster. You can just save this code somewhere and then use it later. So you don't need to like implement every time it comes. Okay. Yeah, a variant of this. So we applied this approach for the power when we are using binary exponentiation. But instead of binary exponentiation, when we are multiplying very big integers, like you have some 10 power 4 digits of integers. So at that time also you can use this thing. So what we are doing then, sorry, so if A is a even, so we are trying to find the product of A into B. So if A is an even integer, so I am saying that this is same as multiplying A by 2 into B and then taking the product with 2. And if A is odd, what we will do that we will find this. Just so if A is odd, we need to find A into B. I will do that A minus 1 into B plus B. So why did I do this? Now A minus 1 becomes even since A was odd. And now I can apply the thing that I was doing earlier. A minus 1 by 2 into B plus B. So you see that this calculation will again take log to the base 2 of A steps, right? And adding this will take O of digit steps. Right? So this had a significant reduction rather than multiplying this both big numbers and getting a O of n squared times time. you reduce the multiplication to log to the base 2 of a. This is not very common thing to implement. This is actually done when we are doing some open source project and you need to implement very big libraries. So at that time, we do this and this techniques, right? So this is it. So any doubts in binary exponentiation? We will be solving some questions at the end, but I guess. Okay, Amit is asking why there are only log n steps. Amit, can you unmute yourself?
Yes, actually,
Yeah, yeah. Yeah, you want to know
yes,
which
yes.
part?
Why there
Yeah,
are
right.
login steps only? I didn't
Yeah,
understand that.
yeah. So you did understand that for calculating, suppose 3 power b, we are finding the binary representation of b as b0 plus b1 plus b0, b1, b2 up to bk. Right? You understand this?
Yes,
Yeah, and we are taking product only for those bits which are set in this number, right? So we see that k is obviously of the order of log to the base 2 of b. You are clear with this part?
yes, yes.
Yeah. So you must understand that for taking the power of 3b0 into 3b1, so on, we will up to 3bk. This is a single step. So once we have this pre-calculated, this product can be done only in one step, right? And there will be only log to the base 2 terms,
Okay,
right? You can understand that because there are b0, b1, b2, and we are taking product k minus 1 time, which is k minus 1 is of the order of log to the base, log b to the base 2. And what is the time for calculating this each power? This is also log to the base 2b. How it is, I had shown that once you have 3 power 1, then we can calculate 3 power 2. Then you can calculate 3 power 4 from this in just single step. This is 3 power 2 into 3 power 2. This is 3 into 3. So these are taking one steps each, and you will do this for k times, where k is log to the base 2b. Right. So what will be your final complexity? Your final complexity will be log base 2b for calculation part and log base 2b for taking these products. Right.
yes, yes.
Yeah. So you have O of log base 2b. You know that in O of notation we exclude the constant powers. So this is order of log. Right. Hope it is
Oh,
clear now.
yes, it is clear.
You can mute yourself. Any other doubts? I guess not. Okay. Cool. So we will now start with matrix exponentiation. Matrix exponentiation is nothing but the implementation of binary exponentiation on matrix. So yeah. First, we will look at what is matrix multiplication. So I found that this example is this example is complete. So like if I explain this, you will understand. So if you are multiplying two matrices of dimension, say 2 cross 3, the first matrix that is 1, 2, 3, 4, 5, 6 is of the dimension 2 cross 3, 2 rows, 3 columns. And the second matrix is of the dimension 3 cross 2, 3 rows, 2 columns, right? So if you are multiplying this, so what is the multiplication procedure? You take the dot product of the first row with the first row of the first matrix with the first row of the first column of the second matrix. That is, you take 1 into 10 plus 2 into 20 plus 3 into 30. First row, first column. For the this creates the first element of your dot product matrix, and then you will do that for the first first row and second column. I will just show you as so yeah. So you have a matrix say A0, A1, A2, A3, and you have the matrix A P0, P1, P2, P3, P4, P5. So the result matrix, you see, this is 2 cross 2 dimension, this is 2 cross 3 dimension. What will be the result matrix? You see that these dimension will always be the same, hence we will ignore this dimension. So the resultant matrix will be of the form 2 cross 3. This and this, right? Resultant matrix will be of the dimension 2 cross 3. What will be its first element? First element will be first row and first column. So this will be A0, B0 plus A1, B3. This will create my first element of this first first row, first column. Similarly, what will be first row, second column of my result? My first row, second column of my result will be first row, second column. So this will be A0, B1 plus A1, B4. B4. This will create my first row, second column. Similarly, you can fill up all the 6 elements. The bottom portions will be first row, first column, first, second row, first column, second row, second column, second row, third column. So you will fill up the bottom. I hope you got the idea of what is matrix multiplication. I had also shared the resources, so you can look back once there also. It's pretty simple how we do matrix multiplication. But why was this matrix multiplication at all important? So matrix multiplication is majorly used to find linear recurrence relation. So like we are most familiar with the Fibonacci sequence. So what is a linear recurrence? Like if I write Fn equals Fn minus 1 plus Fn minus 2, right? So we see that this is linearly related to its to the other terms that came previously to it. But if I had written something like Fn equals Fn minus 1 squared, so this is not linearly related since we have got a quadratic term here, right? So hence linear recurrences are of always of this form. Fn is equals sigma 1 to k some constant ci into f of n minus I. F of n minus I is some previous term that had already come in the sequence of the terms. Also, we can add some polynomial univariate in I. So what is a polynomial univariate in I? So basically we are writing f of k equals f of k minus 1 sorry, f of k minus 1 plus I square plus I plus 1. So this is a polynomial in I, but this is still a linear recurrence. We are doing a square for the term I, not for the term that is a part of the recurrence. Hence, we can put this. This is still a linear recurrence, right? So we are seeing that any function of the type which is linear in the terms of the sequence and maybe a polynomial in the ith element of the sequence. So in this case, this will actually become k instead of I. Since we are talking about the kth term, so it will become k instead of I. Then we will say that it is a linear recurrence relation. So once we have a linear recurrence relation and we need to find the nth term. So what is the most common way of finding the nth term of a sequence? Say I say you have first term as a0 equals 1, a1 equals 2, and you need to find a50. So what will you do? You will keep on calculating like a3 equals a0 plus a1, and then a4 equals, sorry, what a3 equals a2 plus a1, a4 equals a3 plus a2, and so on up to, we will be calculating up to 50 terms, which will take a lot of time even when you are using dynamic programming, right? So what you can do instead is that we will apply a matrix transformation. So this big matrix that you see, that matrix T, is known as a transformation matrix, and F is my current matrix which will contain my current terms. So F0, F1, F2 is the basically my k for starting k terms of the recursion. And once I apply transformation on this on this vector, I will get F1, F2, F3 up to F3. So what is happening, I will show you here. So say my Fibonacci numbers had the terms F0 and F1 for the starting. So I will build my transformation matrix. So I will reverse it. Yes, okay. So I will ignore my this part. I want that after my transformation, I get the next two terms, that is F1 and F2, right? So my transformation, this is a 2 cross 1 matrix, sorry, yeah, 2 cross 1 matrix. This will actually come here. Let's do F1, sorry, let's do F1. 2 cross 1 matrix, and I am getting a 2 cross 1 matrix. So what will be the dimension here? See, I said that this and this dimension are the same. Similarly, this will be the dimension of the first part of this matrix, right? 2. And this dimension should be equal to this dimension. So this will be a 2 cross 2 matrix. Here, this is our transformation matrix. This will be a 2 cross 2 matrix. This is just using the property of that the dimensions of the matrix should be matching for doing a matrix multiplication. Now, if I am transforming x0 f1 into f1 f2, what will we do first? Since the first term is f1 and f1 is available here, first I will capture the f1 term. So for capturing the f1 term, I need to put 0, 1. See if this is clear, because if I put 0, 1, so I will get 0, 1 into f0, f1. So 0 into f0 will eliminate f0 and 1 into f1 will capture f1. So we will get f1. Similarly, for the second term, now you see that f2 will be defined as f1 plus f0. Right. So f1 plus f0 can be written as 1 into f1 plus 1 into f0, right? So basically we will be writing here 1 1, because then this will add 1 into f0 and 1 into f1. So we will basically be, after taking a product, we will be getting f1 in the top part and f1 plus f0 in the bottom part. So what was f1 plus f0 is basically f1 plus f1 f2. This is our required matrix that we needed here, right? So this is just an example of how this transformation matrix has been created. Now you see, sorry, yeah. So now you see the transformation matrix. So whenever we have f0, f1, say k, we have k terms up to fk minus 1. So in the first k minus 1 rows, we will be capturing the next bits. So like I had captured here f1, so I had put the second bit as 1. So if I had been capturing a 3 cross 3 matrix, so f0, f1, f2, right? And I need to transform it into f1, f2, and f3. So I need to capture this 2 from this 2. So for the first row, obviously my bits will be 0, 1, 0, since I'm capturing this part. Right. So when you multiply this by this thing, then you will get 0 into f0, 0 into f0, 1 into f1, and 0 into f2. So this eliminates these terms and we will get f1. Similarly, for if I'm doing for the f2 part, I will do 0, 0, 1. That since my third element was f2, I just need to capture f2. So I will eliminate this two, 0 for f0 and 0 for f1, and capture f2, right? So for the first k minus 1 terms, you will be capturing the first k last k minus 1 elements, that is f1, f2, fk minus 1, since these were my first elements. And for the last row, that is fk, so fk is basically coming from the linear recurrence. So now if I had said that for your linear recurrence, fk is equals 2 into fk minus 1 plus 3 into fk minus 2 plus 4 into 4 into fk minus 3, right? So now see that I am finding f of 3. So f of k minus 1 is basically 3 minus 1 is 2. So I am saying that I need to multiply 2 with f of 2. So 2 will come in the third row, so I will place 2 here. Similarly, I want to multiply 3 with 3 minus 2, that is 1, f of 1. So I will put 3 here. And similarly, I want to multiply 4 with f of 3 minus 3, that is f of 0. So I will put 4 here. Right, you got the idea how this matrix has been created, right? Any doubts of how the matrix has been created? Yeah. So cool. So this is how the matrix will be being created. Mm, just a second. Just a second. So the last row will be ck minus 1, ck minus 2 up to c minus 1. Why is the coefficients in the reverse order? You see that my coefficients were 2, 3, 4, and it gets reversed to as 4, 3, 2 when you write it in the matrix. So hence, if my coefficients are c1, c2, c3 up to ck, so I will write it in just the reverse order ck minus 1, ck minus 2, c1. So you get the gist of how the transformation matrix has been created. So what now I can do is that you see that I will write this matrix as F0 and this as F1. Any doubts? Nice.
Hello,
So I, yeah.
F3 is equal to F1 plus F2, na?
Many like I have created this new definition of F.
Oh, you have created new. Okay, okay.
Yeah, I am writing this with this definition, right? Because if F3 was dependent on two terms, then my matrix would have been of the size of 2 cross 2, right? So now it is dependent on three terms. So this is I'm creating a 3 cross 3 matrix.
Okay, okay.
Okay, you get it? So I will. Okay, let me change the name. I will write this matrix as A0 and this as A1. So you see that the kth element, the third element of AK will be basically f of k plus 2, right? F of k plus 2 is basically third element of AK. So like for A0, the third element is f of 2, that is f of 0 plus 2. Similarly for A1, third element is f of 3, that is f of 0 plus 1 plus 2, that is 3. So if I want to find f of m, so we need to basically calculate a of m, m minus 2. Right. So what is a of m minus 2? A of m minus 2 is, see that a of m minus 2 is basically a of m minus 3 into t. T is basically my transformation matrix. Right. I'm using this thing. So similarly, what is a of m minus 3? A of m minus 3 is again t into a of m minus 4. Right. Similarly, if we keep on doing this recursion, it will happen like t into t into t up until so, up until how many terms will be? The last time we will stop at A0. Since A0 was my given terms, F0, F1, F2 will be given 3 terms for the first regression, and there will be, I guess, m minus 2 terms, right? M minus 2. So you are basically taking t power m minus 2 and doing a matrix product with A0. This will, the third element of this, right? Third element will give you f of m. Right, you get the idea of why we are doing this. So, yeah. So once you get, so we see that finding the product of this transformation matrix, the 0, 1, 1, 1 matrix, transformation matrix product is very important. Since once we get the t power nth element, just multiplying it with the initial vector, we can find what is our nth term of the recurrence, f. So this will become f. Okay, so this is so for the Fibonacci number sequence also I will display this. So Fibonacci number sequence, my transformation matrix was 0, 1, 1, 1, and my f A0 matrix was 0 and 1 for Fibonacci numbers, right? So my A1 will become 0 into 0, 1, and 1 into 0, 1. Right. See that we get the terms of this matrix. Similarly, if I apply this T matrix again on A1, so T into, I'm doing A1, 0, 1, 1, 1, 0, 1, 1, 1. This is A1, we will get 1 into 1 will give 1, and 1 plus 1 will give 2. Right. So see that we get the next two terms of the Fibonacci numbers. So this is basically F0, F1, F1, F2, F2, F3, right? So if we keep on going like this, t power 2a1, t power 3a1, we will get the subsequent terms of the Fibonacci numbers. So if I want to find t power n ai, so see that matrix multiplication will take a complexity O of k cube, where k is basically dimension of this matrix. Also, the property that this transformation matrix is always a square matrix. What is a square matrix? Its dimension will always be of the form k cross k. So, if you want to multiply two matrices t into t, your complexity will go O of k into k for k elements and k for taking the product. So if you know the matrix multiplication algorithm, you will be knowing that why you need three loops to cover that. I will show a code of that. So if you now do n times this thing, you will go O of k cube into n. Right. This is a very big number. Like if n is of the again of the order 10 power 9 plus 7. Instead of doing this, if you take the thing that we did in binary exponentiation, that we take n in its binary parts and just take those powers of t, then this will reduce to k cube log to the base 2 of n. Right. So see that now log base to the 2 of 10 power 9 plus 7 is I guess around 30 or so. You can see the significant reduction from 10 power 9 to 30. So your code will be like running very fast with this. So this is we are explaining that. So you can see on the right hand side what we are doing as a tree structure. So for m into n, m power n, we are pre-computing m power n by 2. Since we need, otherwise we will be calculating m power n by 2 two times. We can pre-compute it once and just take the product as explained in the binary exponentiation part. And on the left hand side bottom, you can see that the complexity has been written as O of k power 3 into log to the base 2 of n. It's just the same thing. I don't think I need to explain this further. Okay, so construction of the matrices. How are we constructing this matrices? I have given some example. So for the first recursion, let's see, f of n is basically, okay, so that will be f of I, not n. F of I is 2 into f of I minus 1 plus 3 into f of I minus 2 plus 4 into f of I minus 3, as it was explained currently. I guess I had given this example only. So first I captured the first element f of 1, then I capture f of 2 using 0, 0, 1. And finally, we see that we write the coefficients of the recursion just in the reverse order. Right, 4 into 3, 4, 3, and 2. Now, I will come to the fact when there is a constant available. So, I will give this example only. 2 into f of I minus 1 and 3 into f of I minus 2. Right? So, yeah, we need to compute this. So what will be my transformation matrix? See that first, this will be depending on two previous terms, that is f of I minus 1. Just a second. Okay. F of, I will write the f of I minus 2 first. F of I minus 2, f of I minus 1, and I will put a new term that is for the constant term, right? Since 5 is there, for constant term, we always put the factor of 1. So what do we need from this thing? We need that the transformation matrix will be, which will be a 3 cross 3 matrix, should transform this into f of I minus 1, f of I, and 1. This last term will always remain the same in case of if there is a constant term added. So for capturing f of I minus 1, what we will add? 0, 1, 0, obviously because it's the second term, so second term set to 1. Now, for capturing 1 in the last position, we will put 0, 0, 1, right? Since it's in the last position. What will be the middle term? So middle term is now basically our transformation term. So now I will be following the above recursion. So it says that 2 into f of I minus 1. So 2 into f of second term, 3 into f of I minus 2, which was the first term. So 3 into f of I minus 2, and 5 into constant, 5 into last term. So you see 0, 1, 0, 3, 2, 5, 0, 0, 1, which is also, see the answer, 0, 1, 0, 3, 2, 5, 0, 0, 1. So once you do that, you see that you will get f of I. So if I take the product of this and this factor down, so I will get 3 into f of I minus 2 plus 2 into f of I minus 1 plus 5 into 1, which will be returning me f of I. F of I had the definition of this. I have the definition. So we get this back using this matrix multiplication, right? Okay, cool. So this was easy example. So let us go to some tougher example. So I said that previously that we can also include something of the form I power 2 and I power 3, so on. That is any polynomial which is in I. Right. So what we will do, like we will be appending 1 for n times. Like if I have the ith power as k, so in this case my k is 2, so I will add 1 for each 0, 1 and 2. That is basically if my polynomial is of the form a0 I power sorry, a0 I power k plus a1 I power uh, k minus 1 up until a k plus 1 I power 0, then I will add 1 for all these k plus 1 terms. Right? All these k plus 1 terms, I will add 1. Even if a1 is 0, I don't care. If a1 is 0 or ak minus 1 is 0, coefficients are 0, I don't care. So since here it was I square, so it can be written as 0 into I power 1 also can be added, and 5 into I power 0. So there are 3 terms, we add 3 ones, 1, 1, 1. And as a similar method, I said first, like we will be transforming F0 to F1, 1, 1, 1. So for the first row, you will be applying the transformation as above. And for the next terms, you will be capturing and applying the transformation by the same method that I had explained. So I guess that yeah, you can try these examples out and see for yourself. You can practice this. I given the now we will talk about some applications. So where are this matrix multiplication questions being applied to? So let us
Can you
first use
can
yeah
you go to the previous slide once?
yeah yeah.
Oh, okay, I have to take the screenshot. Fine.
Oh, I will be sharing this slides. You don't need to take slides. I will be sharing the slides. The slides and the notes. I will share both the things.
Okay.
So let us start with the applications. Where is this matrix multiplication applied, and also see some questions. So counting the number of ways to reach a vertex, right? So what is the problem statement? You are given an unweighted directed graph. I hope you all know what a graph means. A graph is basically a collection of nodes which are connected by some edges, right? So like you are traveling in a city, and the cities then will be your nodes, city A, city B, and the road connecting will be a edge. So this entire network of roads can be written as a graph, city B. So you can read about graphs if you don't know anything. But so we are given an unweighted directed graph. So directed graph means that if an edge has a direction of city B to city C, you cannot go back from city C to city D. The road is only a one-way ticket from B to C, right? And it is unweighted in the sense that the road doesn't have any value attached to it, right? So I need to know the number of ways of reaching the vertex V from U in B steps, right? B is a constant that will be given in B steps. So if it was a single question, you could have done a DFS or brute force type and got the answer. But since you have Q queries which are other of the 10 power 5, and these also quite large, 10 power 9, you will not be doing DFS in each of the queries. So instead, what will you do? you will make a matrix, adjacency matrix. So if you know about graphs, you might know the two representation, adjacency list and adjacency matrix. You will take the adjacency matrix of the graph. This is basically our transformation matrix of the for the graph. And what you will do, you will just take the power of b times. That is multiply the adjacency matrix with it b times, and the result that you will get after multiplying it b times is that is will be your answer. So how can you take t power b is using the binary exponentiation thing, that we binary exponentiation method that we discussed earlier. And why are we taking the product? So like, why is taking the product giving me a result for this? So you see that your matrix, the entry MAB will represent that number of ways of reaching B from. Achha, also, one more note that there may be multiple edges from A to B. So, like, uh, if you have one road, you may have two roads from B to C with different traffic. So, like, a car may go from this road, or if it is busy, the other car may go from this road, right? So, there may be multiple edges on from B to C. So if you see that MAB will store the number of ways to go from A to B, and MBC will store the number of ways for going from B to C. So this was already taught in permutation combination, I guess. Like if you are in station A and you want to go to station B, there are two ways to go, and from B to C, there are three ways to go. So what is the total number of ways to go from A to C using two paths? So it will be basically 2 into 3, right? 6. So basically, hence we are taking the product as MAB into MBC. This will give me the number of ways to uh, go from A to C. Hence we are doing it B times, since every time you do a product, you are increasing the path length by 1. So doing B times will increase the path length by B. So we will know how many exactly B steps where you can reach from A to B. So I have linked the problem statement. You can try this question there in courses. Yeah. So now coming to the nth Fibonacci number, I have given the explanation of the Fibonacci number. How is it working? So yeah, you can if you are using a row matrix instead of the column one I explained, then you need to multiply it in the first part. You can ignore this and follow the method I gave. So basically, fn plus fn plus one is equal to f0 into f1 into p power n, where p is the transformation matrix that I had given. So this is basically explaining the same method. There is also another method which is known as the fast doubling method, but it is not a part of our course. If you like know these two properties, f of 2k and f of 2k plus 1, you are basically doubling in each step. That is, you can go find the value of f of 2k from f of k. So you can read about it. This is not a part of the syllabus. Both work in O of log n steps. Why log n steps? Since see that we were calculating the transformation matrix in log n steps, and each step is taking O of k cube time, where for Fibonacci numbers it will be 2 cross 2 cross 2, 8. 8 is a constant very small, so we will ignore it from O of notation, right? So we will get O of n. So O of log 2 base n, you can calculate the nth term, which is very fast actually. So this is the most common implementation. Okay, this is a very interesting question. You can look at it. So what if nth term is of the order of 10 power 5, right? So if n is of the order of 10 power 5, will your binary exponentiation help much? Actually, if you see that you are taking, when you are taking product of very big numbers, you will be facing. Okay, I will not disclose what is going on. You can actually try this question. I have linked it in the resources part. A DMOG, it's on DMOJ. Try this question. You will get to know what is the problem with when n is 10 power 10 power 5. I have linked the solution here of how I have implemented. Don't look at the solution. Just try to implement first on your own using this. I have also linked the code of matrix multiplication. So if you are not able to implement, you can just look at the solution. Right? So don't look at the solution now of that question. That is very interesting. So next is shortest path with specified number of steps. So what we had discussed previously was the number of paths that you can reach in these steps. Now we are saying we want the shortest path that you can reach. So this is basically implementing the same thing that we did there, but instead of you are making a matrix there with the unweighted graph. So like your matrix content will be 0, 1, 0, 1. So like if there is a path, you will add a 1 to it, or else you will not add a 1. Instead, we have a weighted graph. So your element M A to B will have the distance that you will be traveling from when you go from A to B, and do the same thing, that is take the product B times, since we want to go from U to V in exactly B steps, right? So we are finding what is the shortest path length you can cover in these steps, because each path has a different length. So we will take the product again. So you are basically every time you multiply, you are joining a path, and then take the minimum of the path, you will get the answer. You can try the problem in the link below. It's exactly the same method, of how we are implementing the number of paths. Right. So yeah, some questions are modular arithmetic. Modular arithmetic doesn't have many interesting questions, but like this one, a power b mod p. This is the most common question you will find when you are doing modular arithmetic. So this is simple binary exponentiation. Where will it be implemented? It will be mostly implemented in doing the inverse operation. Otherwise, I don't think so. It will be much there. That is e power p minus 2 will give you the inverse of mod p, right? If p is prime. But this is good, like if you have to implement a power b power c mod p, right? A power b power c mod p. So p can be anything. It's not necessarily a prime number. So what we will be doing, that we will be implementing uh, the Euler's method. So what did the Euler's method specify? Euler's method specify that a power phi of p is congruent to 1 mod p, right? So if I take b power c mod phi p, then I know that this term will give me the answer. Why is that happening? So basically, a power b power c I need to calculate mod p, and I can split it into two parts, that is b power c mod phi p, right? This is one part, into a power b power c divided by phi p floor. So this is basically the remainder, and this is basically the quotient. So you can split it into these two parts, sorry, into phi p. This is in the power, right? Just yeah, into phi p. This is the quotient. This is the remainder when you are dividing by phi p to do b power c. Now you see that this thing can be written as e power phi p whole to the power of b power c phi p. Now we know that under modulo operation, this is 1 from the Euler's theorem. E power phi p is congruent to 1 mod p. So 1 power anything will return 1. So whatever your answer will be, it will come from this part, right? Hence your answer will be a power b power c mod phi p, then take the mod p. Once you get this part, you can do a binary exponentiation on b power c mod phi p. So then you can get the answer easily. Hope that's clear. So another type of question is like, if 5x equals 6 mod 8, then what will be the value of 6? So this is simply x is equal to 6 by 5 mod 8. So I said that for the division part, you need to take the inverse of the remainder. So we need to find 5 inverse under modulo 8. So 5 inverse modulo 8 is 5. Why? Because 5 into 5 is 25, which is mod 8. 5 into 5 mod 8 will give 1. Since 25 minus 24 is 1. So 5 is basically the inverse of 5 under mod 8. So what will be our answer? So we will get 6 into 5 mod 8, that is 6. So basically, if you see that if x is 6, so 5 into 6 will give you 30, and under modulate it gives 6. So yes, our answer was correct. So this was simple. I guess you just needed to find the inverse and multiply it with the number. And one more kind of question that you can see is that, like, you are given 3 power 10 power 5. What will be the last two digits of that? So I have like we just did a power b power c mod p. So last for the last two digits, you just need to change p by 100. And since p was not necessarily prime, we can implement this here also. And you could have directly implemented a binary exponentiation also. That could also have been a correct answer. Right. So these are pretty easy questions on modular arithmetic. Okay, so now let us come to some questions on binary exponentiation. So, what, like, you know what is a permutation, right? So, like, if I say a permutation of 1 to n, so basically you are taking 1 to n natural numbers and then reshuffling it in some order. So, like 1, 3, 2, 4 is a permutation of 4, right? So this can also be written in, like, if you are using zero index numbers, then it will be written as 0 to 1 3, right? 0 to 1 3. So what does applying a permutation to an array mean? So if you have a array a0 e1 e2 e3, right, and you are applying this permutation 0 1 2 3 to this, so what will be the result? So result will be, basically you're saying that take the zeroth element and keep, sorry, I will change the color just a second. Yeah, so it's saying that take the zeroth element and move it to the zeroth element, take the first element and move it to the second position, take the second element and move it to the first position, take the third element and move it to the third position. So take the zeroth element, move it to the zeroth position, so E0. Take the first element, move it to the second position, E1. Take the second element, move it to the first position, that is E2, and take the third element and move it to the third position, that is E3. So once you apply this permutation over this array, you are getting this new array, right? So one of the most important application of this permutation is, you must have heard about left shift and right shift of an array. So what is happening when you are doing a left shift of an array, A0, A1, A2, A3? So when you left shift an array, you shift this array this side, right, towards the left. So what will happen that you have A1, A2, A3 shifted one towards the left. And what will happen to A0? A0 will go back. So A0 will come back here. So what is this transformation? So we are also doing a transformation here of a permutation. So this permutation of left shift can be defined as 1, 2, 3, 0. What is 1, 2, 3, 0? 1, 2, 3, 0 is take the zeroth element, take the, have I written correctly? Yeah, sorry. Take the first element and move it to the zeroth position here. Take the second element, move it to the first position here. Take the third element, move it to the second position, and take the zeroth element and move it to the fourth position. See, these are basically the third position. Right? These are basically the final position of the elements, right? These are basically the final position of the elements. How do I explain it? Oh, actually, I had explained this wrong. Sorry, I will explain this. Just bear with me. So what is happening here? If you are applying a transformation of the form 2 0 to 1 3, so you are, these are basically the final positions of the element, right? So 0 1 2 3. So take the zeroth element, put it in the zeroth element, take the second element, put it in the first position, take the first element, put it in the second position, take the third element, put it in the third position. So A0 will now go to the zeroth position, A0. A1 will go to the second. Okay, it doesn't make a change still. A1 will go to the second position, and A2 will go to the first position. A3 will go to the third position. Same as before. Okay. Fine. So you get the gist of how left shift was operated when we applied the permutation. So when you are given a permutation, these are basically the final position of the elements. So if you, okay, now if you apply this one more time, on this. That is, you are applying 1, 2, 3, 0 one more time. So what will happen? Now your first element will be A2. So A2 to the first 0th position, A3 to the second position, A0 to the third position, and A1 to the last position. Right? So you see that when you applied two times, there were two left shift operation. So if I name this transformation as A, then we have basically applied A square on this array, right? So if someone asks you to find the array after k rotations of this k left rotations of A0, A1, A2, A3, you basically need to find A of k into your original ARR, right? So for finding A of k, what will yeah, I have explained the easy in the example also same. So yeah, so for finding AK, what will you do? For finding A power K is again, basically you are doing a power operator. So break the K into its binary parts, 1, 0, 1, 1, something binary, and do a binary exponentiation on this K. So it will reduce from O of K to O of log 2K steps. Right? Okay. If you are not clear with the permutation, I will link the resources. You can go through it again. But permutation is basically simply repositioning the elements as per the given array. These are the final position of the elements. This should be easy enough. Yeah. Now the sixth application is fast geometric operations, right? Fast geometric operations. So we will be considering three types of operation: shift operation, scaling operation, rotation operation, transformation operation. So what is this operation? Shift operation. Suppose a point is at x comma y, right? And we need to shift it to x plus 1 comma y. Right. So this is known as a shift operation. What is a scaling operation? Suppose a line is of length x comma y to x plus 1 comma y, and we need to scale this line to 2 units. This is 1 unit. I need to scale it 2 units with starting at x comma y. Right? X comma y is the starting point, and I need to scale it 2 units. So where will this go? X plus 2 comma y. Sorry, actually this should be horizontal line, but just get the point that since we are scaling it 2, so the coordinate will increase by 1. This is known as the scaling operation. Finally, what is the rotation operation? So rotation operation is if an array is at a angle of say 40 degrees, 40 degrees with the x-axis, and if point is here, right, point is x comma y, and I need to rotate it to a new point, say 65 degree, and find the new position as x1 comma y1, then this operation is known as the rotation operation. So these operations can again be done using the transformation matrix. So these operations have transformation matrix defined. So like I had explained how to find the matrix in the recursion. Similar method can be done for the transformation also. So like I have given an example here that shift x. So we are considering a three-dimension matrix, right? You see that the transformation above will always be of the form xyz for the three coordinates and one for the constant. Like if we want to add some constant to x, add some constant to y for the shift operation, so we put a one for that one. So for the shift operation, we do that. We want to shift x by 5, y by 7, and z by 9. Right. So you see that since the constant is in the last row, we will put all the factors by which we need to shift in the last row, and on the main diagonal will always be 1 since it's the capturing element. This is our transformation matrix for the shift operation, right? For the shift operation. Where will the main diagonal come into action? The main diagonal will come into action when you want to scale the elements. When you want to scale the elements, you see that all other elements will be 0 since we are not shifting. So the last three elements of the row, you can see that they will come into action only when, suppose you were doing with shifting plus scaling. So if you were doing the previous transformation, that is shift x by 5, y by 7, and z by 9, along with this new transformation, then it would have been 10, 5, 5, 1, 0, 0, 0, sorry, yeah, 0, 0, 0, 0, 0. And here it will come the shift operation, that is 579. What is this? This is basically transform. What transformation are we applying? So the transformation we are applying is that we are scaling plus shifting. So this part is for shifting, and this mean diagonal is for scaling. Right? Mean diagonal is for scaling. So rotation is quite complex. So rotation is usually used independently. You need to memorize this part. I guess you have used this in the G times cos theta minus sin theta and sin theta plus cos theta as a rotational transformation. But it's better to usually memorize this rotations transformation matrix. It's difficult to derive during the computation hours. So, yeah. That's all I had for this session, I guess. So I have covered all the questions. Yeah. So I have linked quite many questions on the topics that we have discussed now, and I have also linked some references also. Please try those questions. And yeah, you see that there is a D emoji Fibonacci sequence harder on my right hand side in blue. That is the question that I have asked you to try it on your own without seeing the solution. Try it when you are free. Very interesting question. You will get to know what was the issue. If you are not able to solve any of the questions, you can just ping me. I will help you out. So that's all for the session. Thank you. Stay tuned for more classes. I will stop the recording now. And if you have any doubts, please ask now.